Yes, thank you so much. Can I share some information about you? Uh,
Yes, please.
Hello, everyone. There is the next session. My name is Anna. I'm a researcher at Institute of Missile Physics and Ural Federal University at Yekaterinburg, Russia. And also our co-chair will be René Morales from Leibniz University at Hanover, Germany, and Carmen Stefana Clemente from Department of Engineering, University of Sanioi, Italy. You can ask your questions in chat by raising your hand or simply turning on the microphone. I would like to introduce our distinguished speaker, Xichao Zhang. He's a postdoctoral fellow at the Department of Electrical and Computer Engineering at Shinshu University, Japan. He received his PhD degree from Shinshu University in 2018. His research focused on the theoretical study of topological spin textures and dynamics, and he co-authored more than 90 peer-reviewed papers. He serves as a guest editor of Journal of Magnetism and Magnetic Materials and of Magnetism, and guest associate editor of Frontiers in Physics. The title of the report is Frustrated Skyrmions, Bimerons, and Skyrmion Strings. You're welcome.
Okay, so let me open the presenter view. All right, so
yes.
Do you see my laser pointing? Okay, right. Okay, so thank you for the introduction, and I also want to thank the conference committee for inviting me to join this very nice online conference. So today I will talk about my theoretical study of frustrated skyrmions, bimerons, and three-dimensional skyrmion strings. So this is an outline of my talk. In the first part, I will briefly introduce magnetic skyrmions and the frustrated spin systems. In the second part, I will talk about my research results on frustrated skyrmions and bimerons, including some static properties and the dynamics driven by the spin currents. And I will also give an outlook on future study of topological spin textures in magnetic systems. At the beginning of my talk, I would like to thank my collaborators on my frustrated skyrmion projects. And I also want to thank my collaborators on other skyrmion and spintronics projects. And my research was supported by the Japan Society for the Promotion of Science. Okay, so before talking about the magnetic skyrmions, I want to show you first show you some pictures about the vortex structure. This is because the skyrmion is just like a vortex structure. The vortex structure is very famous in our universe. It can be found in the nanoscale magnetic materials. And it can also be found in the water, such as the very famous Naruto whirlpools in Japan. And some galaxies in our universe also show the vortex structure. So this year, I also found a vortex structure on my baby's head. In fact, in a topological space, the structure of a skyrmion can be regarded as a combination of two vortex structures. So generally speaking, the magnetic skyrmion is a nanoscale or microscale non-collinear spin texture. The skyrmion carries some topological information and can be regarded as a quasi-particle due to its topological nature. The concept of skyrmion was initially proposed by Tony Skyrm 60 years ago in the field of nuclear physics. But the theoretical prediction of skyrmions in magnetic materials was made by Bogdanov and his co-authors in 1989. And after 20 years, in 2009, the magnetic skyrmion was for the first time observed in chiral magnets as the A phase in this phase diagram, where A stands for anomalous. So here, I also want to mention that the topic of magnetic skirming is related to some important research areas, including the fields of spintronics, topology in physics, and the complex systems. This is because magnetic skirming is a spintronic object. It also has a topological structure. And many magnetic skirmings, especially those can be treated as rigid particles, can also form complex systems and show complicated dynamic behaviors due to the interactions between skirmings and the pinning sites. Okay, so in order to describe the magnetic structure of a skirming, we need to introduce the skirming number, which is also called the topological charge in some published papers. However, different skirming textures may have the same skirming number, so we also need to introduce the vorticity and the helicity numbers. Here, I don't go into the details, but the key point is that the vorticity and the helicity numbers can fully describe the relation between the spin orientation and the position of each spin for the spin texture. For example, you can see this neo-type skirming and the block-type skirming have the same vorticity and the skirming number, but their helicity is different. So with the skirming number, vorticity number, and the helicity number, we can fully describe a topological spin texture. For example, we can use the skirming number to tell the general topological information carried by the spin texture. And then we can use the psi of the vorticity number to define the skirming and anti-skirming state. And we can also use the helicity number to distinguish the neo-type and the block-type skirming. On the other hand, I want to point out that the magnetic skirmings are stabilized in perpendicularly magnetized systems. In the in-plane magnetized systems, we can also find some topological spin textures. The basic topological spin texture in the two-dimensional thin film with chiral exchange interactions is a so-called bimeron. The bimeron is a pair of two merons. The bimeron can be seen as a topological counterpart of the skirming because they could have the same skirming number. And the skirming and bimeron could have the same topological structure, but their dynamics may be different, which I will talk later. Here, I want to let you know that the skirming was named after Tony Skirm, and the terminology meron was initially derived from the Greek root mero, which means part or fraction. This is simply because the meron texture carries a half-unit topological charge. Okay, so since the first observation of skirmings in 2009, the magnetic skirmings has been a very hot topic, and more groups have joined this field of study. Basically, in the field focused on the skirmings at low temperature and the high magnetic field. Since 2015, the magnetic skirmings have been realized at room temperature in magnetic multilayers, and in recent years, a number of device applications have been proposed based on skirmings. For example, in the past 3 years, we can see many lower applications based on skirmings have been proposed, such as most are about using skirmings for computing, such as neuromorphic computing and even for the quantum computing. Here, I want to mention that the advantages of using skirmings as information carriers in storage and computing applications include three major points. First, the skirming can be as small as a few nanometers, which means the storage density of a skirming-based memory could be very high. Second, the skirming can be driven into very fast motion by electric currents, which means it can be used for ultra-fast operation in spintronic devices. Third, the skirming is a rigid object and could have an ultra low power consumption. So it means skirming can also be used to build a device with low power consumption. Okay, so in order to stabilize topological spin textures in magnetic materials, we need to have some special interactions such as the Janosky-Monier interaction. This is because the normal ferromagnetic exchange interaction only favors the parallel or anti-parallel alignment between two adjacent spins, so it cannot stabilize the non-collinear topological spin textures. However, the Janosky-Monier interaction favors an angle between two adjacent spins, so the competition between the Janosky-Monier interaction and the ferromagnetic exchange interaction may result in the generation of some topological spin textures in the magnetic materials. In fact, some other interactions are also able to stabilize topological spin textures. In this talk, I will focus on the topological spin textures stabilized by the frustrated exchange interactions. What is a frustrated spin system and why can it stabilize topological spin textures? Let's first consider a simple triangular lattice with 3 Ising-like spins and anti-ferromagnetic exchange interactions. If the blue ball is a spin up state and the green ball is a spin down state, so what is the state of the third spin? Obviously, you will find it can be either a spin up or spin down state because the two states have the same energy. So we can see this system has some degenerate states, and we think it is a typical frustrated spin system. Here I want to show you another example of the frustrated spin system. That is a chain of Ising-like spins with the nearest neighbor ferromagnetic exchange interaction and the second nearest neighbor anti-ferromagnetic exchange interaction. And in this system, the competition between the two exchange interactions we also lead to a frustrated spin system where we can find some degenerate states. So in the frustrated spin system, the exchange frustration is very important and could be able to generate some non-trivial topological spin textures. Okay, so since 10 years ago, the existence and stabilization of magnetic skirmings by frustrated exchange interactions have been suggested by some theoretical works. And in these works, skirmings are stabilized by competing ferromagnetic and anti-ferromagnetic exchange interactions in the presence of some perpendicular magnetic anisotropy or magnetic field. In this slide, I list some selected papers on frustrated skirmings published in recent 10 years for your information. Most are theoretical and simulation works. If you are interested in these papers, I can send you a copy of this slide after the conference, or you can find a video of this talk on the conference YouTube channel. Here, I want to emphasize that the field-induced and the current-induced dynamics of frustrated skirmings have also been studied in some theoretical papers. And an important dynamic feature of the frustrated skirmings is the coupling between the center of mass dynamics and its helicity dynamics. For example, in this slide, I show you 2 videos about the current-induced motion of a frustrated skirming and the current-induced motion of a normal skirming stabilized by the Janosky-Monier interaction. You can see that the frustrated skirming moves in a circular path and its helicity varies with time. But the normal skirming stabilized by the Janosky-Monier interaction moves along a straight line, and its helicity is determined and fixed by the Janosky-Monier interaction. So in our group since 2016, we have been working on the study of frustrated skirming dynamics. And in recent 2 years, we are also working on the dynamics of some other topological spin textures in fast radial spin system, such as the bimerons and the three-dimensional Skyrmion strings. Okay, so the first work I want to talk is about the fast radial skirmings in a two-dimensional magnetic thin field, where skirmings are stabilized by exchanging frustration in a system with dipole-dipole interactions. In this study of fast radial skirmings, I'm focusing on the skirming dynamics in a square lattice of J1, J2, J3 model studied by Lin and Hayami, where the J1 is a ferromagnetic exchange interaction, and the J2 and the J3 are antiferromagnetic exchange interactions. I also include the perpendicular magnetic anisotropy, the perpendicular magnetic field, and most importantly, we consider the effect of dipole-dipole interaction. The magnetization dynamics is controlled by the LLG equation with the damping-like spin torque. The damping-like spin torque can be generated by some ways such as the spin Hall effect. So as the first step, we study the metastability phase diagram of relaxed spin textures for different parameters. And this figure shows the relaxed spin textures from a random initial spin configuration. You can see that different types of skirmings or anti-skirmings can be stabilized at certain values of perpendicular field or magnetic anisotropy. So we continue to study the energy of skirmings and the function of the helicity number because the helicity is an important degree of freedom in the fast radial skirming system. So in previous published reports, the skirming energy doesn't depend on its helicity in the absence of dipole-dipole interactions. However, in our study, we find that if we consider the dipole-dipole interaction energy in the simulation, the energy of skirmings with the skirming number of 1 and 3 will be dependent of the helicity number. In particular, we focus on the skirming with the skirming number of 1, and you can see the block type skirmings are favored by the dipole-dipole interaction energy. We also find that for the skirmings with the skirming number of 1 and the different helicity ranging from 0 to 2 pi, most skirmings will relax to block type skirmings unless it is a standard Leo type skirmings before the relaxation. That is to say, the block type and the Leo type skirmings are metastable states in fast radial spin system, but the block type skirmings are more stable than the Leo type skirmings. Okay, so what is more important and interesting is the dynamics of fast radial skirmings driven by the damping-like spin torque. The current induced dynamics of fast radial skirmings in the absence of dipole-dipole interaction have been reported by Lin and Hayami in this PRB paper. And the key feature of the dynamics is that the skirming moves in a circular path, and its helicity also varies with the time because it is coupled to the center of mass dynamics. However, we find if we include the dipole-dipole interaction in the simulation, the block type skirmings will be more stable than the Leo type skirmings. So at a small current, the skirming moves in a straight line with the block type helicity. This is just the same as the skirming dynamics in ferromagnetic thin films with Janositsky-Monier interactions. However, when a large current is applied to drive the skirming can overcome the energy barrier between different helicities. So it shows a circular motion, and its helicity jumps between the block and the Leo types. Okay, so because there are two different block type skirmings in the fast radial spin systems, that is clockwise and the counterclockwise configurations. So we think we should be able to see the skirming Hall effect of fast radial skirmings when a small current is applied to drive the skirmings. That is to say, we may find the accumulation of block-type skirmings at the opposite edges of the sample when the current is applied for some time. I think this is something someone could try to realize in experiments in the future. In theory, we can also control the direction of motion of a frustrated skirming by tuning the amplitude of the driving current density. For example, the skirming first moves toward the right direction driven by a small current. And if we suddenly increase the current density for a while, the rotational mode will be excited, and then we can use it to change the direction, the helicity and the direction of motion of the skirming. In this work, we also find that two adjacent frustrated skirmings can merge into a single skirming. This can be treated as a bound state of skirmings. The merging of the two skirmings is subject to the relative helicity configurations of the two skirmings. That is to say, if you want to merge the two skirmings, you will need to put them close to each other, and they should have opposite helicity numbers. Also, by applying a spin current, we are able to split the skirming with a skirming number of 2 into two skirmings with a skirming number of 1. This dynamic behavior is fundamental for the manipulation of a 3-dimensional skirming string with a high skirming number, which I will talk later. Okay, so the second work I want to introduce in this talk is about the frustrated bimerons in 2-dimensional magnetic thin films. The bimeron are topological counterparts of skirmings, but they could have different dynamic behaviors. In the study of frustrated bimerons, we also consider a simple square lattice with 3 competing exchange interactions based on the system studied by Lin and Hayami. And the exchange interaction G1 is ferromagnetic, and G2 and G3 are anti-ferromagnetic exchange interactions. We also consider the in-plane z-axis magnetic anisotropy, applied magnetic field, and the effect of dipole-dipole interaction. We first studied the static structures and energies of bimerons with different vorticity and helicity numbers. We also compare the bimeron results with that of the frustrated skirmings, and the parameters used for the bimeron and the skirming system are the same. You can find it in the paper. The only difference is the direction of the z-axis as indicated below the figure. For the skirming system, the z-axis is pointing at the z direction, and for the bimeron system, the z-axis is pointing at the x direction. For the relaxed bimerons and the skirmings, both the bimeron energy and the skirming energy depend on their helicity numbers. For the skirming, I have mentioned before that the total energy reaches the minimal value at the helicity of 0.5 or 1.5 in the units of pi, because the block type spin textures are favored by the dipole-dipole interaction. But for the bimeron texture, the total energy reaches the minimal value and the helicity configuration of 0 and pi. This is because the bimeron texture with the helicity numbers of 0 and pi will show block type structures in the studied systems. And if we turn off the dipole-dipole interaction in our simulations, both the skirming and bimeron energy will be independent of the helicity. We also compare the total energy of a relaxed bimeron and the skirming and the function of the vorticity number. And we find the total energy of the bimeron and the skirming increases with the absolute value of its vorticity number, and the size of the bimeron and the skirming also increases with the vorticity number. In this slide, the two figures on the left side show the contribution of different energy terms to the total energy of relaxed bimeron or skirming with a vorticity number of +1. The difference between the bimeron and the skirming energies is that the dipole-dipole interaction energy of the bimeron is much smaller. This is because the dipolar interaction is naturally stronger in the perpendicularly magnetized system. So the skirming system has a larger dipole-dipole interaction energy. On the other hand, the two figures on the right side show the different energy terms of bimeron or skirming as functions of the vorticity number. The difference between the bimeron and the skirming is also the dipole-dipole interaction energy. The dipole-dipole interaction energy of the skirming decreases with increasing vorticity number, but for the bimeron, the dipole-dipole interaction energy increases with the vorticity number. And in this work, we also studied the bimeron dynamics induced by the damping-like spin torque. And the bimeron dynamics is much more complex than the skirming dynamics because it depends on the orientation of the spin polarization and to the z-axis. The dynamics of bimeron is when the spin polarization is perpendicular to the z-axis, the dynamics of bimeron is similar to that of the frustrated skirmings. That is, a small current will lead to the straight motion, and a large current will lead to the elliptical motion of the bimeron. And the three figures on the left side show the bimeron velocity, the skirming Hall angle of the bimeron, and the average helicity of bimeron, and the functions of the applied current density. You can see that there is a critical current density beyond which the bimeron dynamics transition from the straight motion to elliptical motion will happen. Here I also want to mention that for the straight motion of bimeron induced by a small current, the motion directions of the bimeron with opposite skirming numbers are symmetric with respect to the z-axis. We also studied the effect of field-like torque on the bimeron dynamics when the spin polarization is perpendicular to the z-axis. The most important result we find is that the field-like torque may result in the deformation of the bimeron and further result in the dynamics transition from the straight motion to the elliptical motion. And when the bimeron shows the elliptical motion, the frequency of the elliptical motion is found to increases with the field-like torque strength. But at some point, the field-like torque may destroy the bimeron. Okay, so when the spin polarization is parallel to the z-axis, we find the damping-like torque cannot drive the bimeron into motion, but the spin torque will result in the rotation of the bimeron with respect to its center. And we find that the frequency of the rotation is proportional to the applied current density. In this work, we also studied the current-induced dynamics of a cluster-like bimeron state with a large vorticity number. We first find that the cluster-like bimeron texture cannot be driven into motion by the damping-like spin torque when the spin polarization is perpendicular to the z-axis. So we use a small current and to drive a single bimeron toward a bimeron cluster. And we find that when the two spin textures meet each other, they will be merged into a new state, and the total skirming number of the system remains unchanged. For example, the merging of a cluster like bimeron with the vorticity number of +4 and a bimion with the vorticity number of +1 will result in the generation of a cluster like bimion with the vorticity number of +5. And the merging of a cluster like bimion with the vorticity number of +4 and a bimion with the vorticity number of -1 will result in the generation of a cluster like bimion state with the vorticity number of +3. Okay, so the last work I want to briefly talk is about the dynamics of Skyrmion strings in three-dimensional magnetic multilayers. So in this work, we consider a multilayer of 20 frustrated magnetic thin films with weak ferromagnetic interlayer exchange interactions. And in each magnetic layer, we consider the G1, G2, G3 exchange interactions similar to the two-dimensional case. Previously, I have mentioned that frustrated skirming with a skirming number of two can be transformed to two skirmings with a skirming number of 1, driven by the spinning torque. This motivates our current study on the bifurcation dynamics of a skirming string. So first, we apply a current pulse to drive all magnetic layers, and where a skirming string with a skirming number of 2 is initially relaxed at the center of the multilayer. And in such a case, the frustrated skirming in each magnetic layer driven by the spin torque will be divided into 2 skirmings. So the skirming string with a skirming number of 2 is transformed to 2 skirming strings with a skirming number of 1. And when the current pulse is off, the 2 skirming strings will be relaxed in the multilayer. So what is more interesting is that if we only apply the pulse current to the top half or bottom half of the multilayer, the spin torque will drive the skirmings in the top half or bottom half of the multilayer into the dynamic transformation. And due to the interlayer exchange coupling between adjacent magnetic layers, you will find that the skirming string with a skirming number of 2 can be bifurcated into a Y-shaped skirming string where the 2 branches carry the skirming number of 1. In similar ways, if we apply the current pulse to both the top and bottom 5 layers of the multilayer and assume no current injection in the middle 10 layers, we will get the skirming string bifurcated into an X-shaped skirming string with 4 branches. And if we only apply the current pulse to the middle 10 layers and assume low current injection in the top and the bottom 5 layers, we will get the skirming string bifurcated into an O-shaped skirming string. And finally, I want to point out that the bifurcation operation should be universal to any stable or metastable skirming strings with a skirming number larger than 1. For example, if we apply the current pulse to the top 10 layers of the multilayer, where a skirming string with a skirming number of 3 is initially relaxed at the multilayer film center, we will get the skirming string bifurcated into a skirming string with 3 branches. Okay, so in this slide, I show you a brief summary and outlook on future research. In this talk, I only focus on the skirming and bimion textures in frustrated magnetic systems. So in the future, asking more attention and effort should be devoted to different 2-dimensional and 3-dimensional topological spin textures in different magnetic materials. And on the other hand, I think we have many different ways to interact with the spin textures. So in this work, I only use the damping like a spin torque to control the skirming and the bimions. So in the future, I think maybe we can try to study the frustrated topological spin textures controlled by such as spin waves and electric field or thermal effect. And I also think there are also some published papers on frustrated skirmings driven by the spin waves. I think the ultimate goal of the skirming research is to uncover the skirming physics in different systems and develop the skirming-based spintronic devices that can be used for information storage or logic computing. In this slide, I show you some different types of topological spin textures. Some are two-dimensional and some are three-dimensional. In the past 10 years, I think most researchers in the field are focusing on the basic skirming textures in two-dimensional thin film or multi-layers. So in the future, I think it is important to explore the possibility of using other types of three-dimensional topological spin textures in spintronic and electronic devices. So it is also very important to study the fundamental physical properties of different three-dimensional topological spin textures, such as the different types of skirming strings and the bimeron strings. The topological spin textures with a large skirming number are also very interesting and should be studied, but the stability of the spin textures carry very high topological charge and could be a problem. Okay, so I also think it's important to investigate the pinning and the depinning physics of different two-dimensional and three-dimensional topological spin textures on different pinning patterns, especially in the three-dimensional nanostructures. This is because we could have different types of pinning structures in the three-dimensional nanostructures. So the dynamics of three-dimensional spin texture interacting with three-dimensional pinning will be very complicated, but I think it can generate some interesting results. Okay, so before ending my talk, I want to let you know that we are currently organizing a special issue on topological spin textures in the MDBI magnetism journal. If you want to contribute your paper to this special issue, please contact me or other guest editors, and you can find my email address on this slide. And this year, we are also organizing a special issue on magnetic materials for 5G and beyond 5G applications in the Journal of IEEE. If you want to contribute a paper to this special issue, please also feel free to contact me or other guest editors. Okay, so thank you for your attention.
Thank you very much.
Sorry, I can't
Thank you
hear.
very much.
Yeah.
There was lots of questions during your talk, some of them really controversial. I start at the beginning.
Okay, so let me check the chat board.
What does OP represent in Skyrmion number integral?
Yeah, so this, let me go back to the slide. So I think it should be this. Yeah, so this equation is a definition of the topological charge for two-dimensional case. So when you have a topological skirming, maybe you can. So this part could be the density of the skirming, and if you do the integral, you may get 4 pi for skirming texture, and so you need to have have this Skyrming number over 4 pi and to get a integer number and to stand for the topological charge. Yeah, I think maybe you can find some mathematical details in this review paper published in JPCM. In the section 1, you will find the math details on the definition of the Skyrming number or Skyrming number density. Yeah.
Okay, thank you so much. The next question is, does the Shinshu-Mori interaction exist without heavy metal? Means inside some insulator.
Yeah, so basically, I think there are two groups of people working on the DMI materials. Someone working on the system where the DMI is induced and the interface in the multilayer, and some working on the system with asymmetric lattice structure. So the DMI is generated due to the Balkan inversion symmetry in the materials. So I think you mean the system with heavy metal is a system such as a multilayer or the materials prepared by the magnetron sputtering. But in some bulk chiral magnets, you can have the DMI due to the Balkan inversion symmetry of the materials. But I'm not sure about the insulator because I only work on simulations. Yeah, maybe you can ask experimental researcher about this question.
The question is, can pinning destroy the skyrmion in a racetrack?
Yes. The pinning, maybe impurities in the nanotrack or defect in the nanotrack can destroy the skyrming if the skyrming touches the pinning, but it also depends on the situation. Some pinning is attractive for the skyrming. Some pinning is will provide a repulsive force. So this depends on the situation of the pinning, and there are, I think there are a number of papers about the interactions between skyrmings and pinning. I think maybe you can read Jan Milner's paper in PRB, which is about the interaction between the skyrming and the hole in the nanotrack. And if you want to know more about the pinning in physics in skyrming systems, maybe you can read Charles Richard's paper. They have published many papers using the particle model to study the system where the number of skyrmings are interacting with pinning. Okay.
I mixed some question. The next one will be for the collision, slide 41. Do you need to pin one of them, or are the velocities a difference?
What difference?
Do you need to pin one of the spin, or not spin, bimerons, I think, or are the velocities that's different for the collision?
Yeah. So which questions? I'm searching the chat board.
I can resend it to you.
Yeah, yes, it is. Page 41. Okay, let's go back to page 41. Okay. 41. This one? Okay. Do you need to pin one of them or the velocity? Yeah, in such a system, we don't need to pin the bimerion cluster because the bimerion texture with vorticity number larger than 1 cannot be driven into motion by the damping like spin torque. So in such a system, we just put a cluster-like texture on the left side and a single bimerion texture on the right side, and we apply the damping like spin torque in the system, and only the bimeron texture with the Skyrmion number of 1 can be driven into motion toward the cluster. So we don't need to pin the cluster like texture because it cannot be driven into motion. Yeah.
Thank you so
That means,
much. And I think,
yeah.
sorry.
Yeah. Yeah.
I think
Yeah,
the
go
last
ahead.
question will be, in what materials and geometries could we expect these textures with high Q?
Yeah, so I think this is another question I cannot give you a perfect answer because I don't know work on experiments. So but from the viewpoint of theoretical simulations, I think if you want to have a high Q, high Skyrmion number texture, that means such a texture should be a metastable or stable state in the system. But there is a basic rule is that the energy of the Skyrmion texture increases with the Skyrmion number. That means, for example, if you have Skyrmion number 1 and 2 and 3 in the system, maybe the Skyrmion with Skyrmion number of 1 is the ground state and other state will be the excited states. In such a case, the skirmings with a high Skyrmion number may be easily destroyed due to such as the thermal effects. So sometimes it will be difficult to have topological spin textures with a high topological number. Yeah, but I think there should be some materials you can stabilize the Skyrmion textures with a high topological number.
Okay, thank you so much.
Yeah.
I'm forced to close the discussion on Zoom and invite the lecturer and interested participants for further discussion gather down. I remind you that in order to view the poster, you need to press X, and I remind you that in your free time you can watch poster reports. The next session will start in 2.5 hours, as well as watch and vote for art and memes